So, thanks everybody for coming this afternoon. So, today we have Daniele Vilone here. He did the PhD in Rome with the Vilone group there, with Vittorio Loreto, Claudio Castellano, and al, working on the Volta model from the theoretical point of view as a simulation, right? Then he moved to Florence and from there he tried the private business in petrol with Exxon in Prague.
Yes, then also went to Bremen.
And then to Bremen, and now he has a postdoctoral position in Madrid in the Universidad Carlos III with Ancho, working on the topic of the presentation, the topology and the cooperation. So this topic that also we have worked a little bit on that. So he's just visiting us for today. So if you want to talk with him, so this has to be this afternoon. So thanks for coming.
Thank you for the invitation. Okay, this is the title. I'm going to talk about the role of topology in the evolution of cooperation and also the role of other mechanisms for the evolution of cooperation. But yes, step by step, it doesn't work. It was working before. No? See? Okay, some introductory concept on game theory and evolutionary dynamics. I don't know how much do you know about these topics. Then I will introduce some social dilemmas and the connection with game theory. First step is what happens in well-mixed populations. It is in populations where individuals are all connected among them. And then we'll see what happens in lattices and random topologies. Then we'll draw some conclusions and perspectives, and I will talk briefly also about another problem inherent to the evolution of cooperation. That is what happens with discrete time dynamics. Okay, what's the problem? The problem is the emergence of cooperation. So, we know that from an evolutionary point of view, selection of the fittest, at level of individuals in nature, but also in human societies, cooperative behavior are not the most convenient for individuals. But at the level of populations, we see that cooperation is always selected by populations in nature and human society. This is a sentence by Darwin that actually says that. So, how can individuals, how can altruists can reach the age to reproduce? Because it seems that this behavior is not enhanced by natural selection at level of individuals. Well, this was said to be one of the 25 problems for the 21st century. I don't know why, but anyway, this is a very debated problem. A mathematical approach to this problem is to search for some model that explains this phenomenon. So, cooperative behaviors that are suppressed at level of interaction between two individuals that can spread throughout a population. Okay, the first hypothesis was that special structure can enhance this, the emergence of such behaviors. This was firstly proposed by Novak and May in '92, and so coordination between network reciprocity or also topological features were suggested to be the mechanism by means of which cooperation can overcome the difficulties at level of individuals and spread through a very large population. But okay, let's go step by step. Now we introduce the two times two symmetric social dilemmas. So the first thing is, okay, let's think to just two players. Each player can adopt one of two possible strategies: cooperate or defect. This is the payoff matrix. So in the rows tell us the payoff of the player according its strategy and the strategy of the opponent, because the payoffs the fitness what the player earned for an interaction with the opponent is given by this matrix. For example, if the player cooperates and also the opponent cooperates, he earns 1, some unit. If the opponent defects, the payoff is S, or if the player defects when the opponent cooperates is T, or 0 in case of mutual defection. T and S are the parameters of the game. If T is larger than 1, we have a temptation to defect, because in case the opponent cooperates, it would be more convenient to defect. And analogously, S less than 0 means a risk in cooperation. Usually, T and S are bounded. Until now, at least T has been considered between minus 0 and 2, and S can go from minus 1 to plus 1.
Excuse me.
Yeah?
So why is it you call it symmetric and then S and T?
Symmetric because, okay, the other opponent has the same payoff matrix. So if one player, for example, defects and the second one cooperates, the defector gets T and the cooperator S. If they change,
I understand that.
Okay. So, according to the value of the parameters, we have 4 classes of games. Here, harmony, class of harmony games, are the games where we have no tensions, there's no risk in cooperation, no temptation to defect. it's the easiest. Then the opposite, we have the prisoner's dilemma game, which will be the game we will focus on. That has both tensions, so temptation to defect, but also a risk in cooperation. We have two intermediate classes, the Stag Hunt, coordination, or the other class that depends on the precise values of the parameters. The game has different names, for example, Snowdrift, Hot Dog, Battle of Sex, and so on. But anyway, qualitatively, the games can be defined in these four classes. Okay. What happens when we have not just two players that play one shot, but a population of a great deal of individuals that play among each other, and then they have to reproduce because we want to modelize, I don't know, an ecosystem or something similar. In this case, we have to define, for example, the density of cooperators, or individuals that use a cooperation, the strategy of cooperation, XC. What is the dynamics of this density? First, for the moment, we focus on well-mixed population. That is population where individuals are directly connected all each other. So every individual interacts with everyone else. Well-mixed population, or it's just a mean field approach. Then individuals reproduce according to payoff accumulated after a round of games with everybody else. So bigger is the payoff accumulated, and larger is the probability to reproduce. In the opposite case, less is the payoff accumulated, and larger is the probability not to reproduce. For the population, the dynamics is ruled by this replicator equation that can be written in these two equivalent forms, which says that the rate of changement of the density, so how the density changes in time is proportional to the density itself. So if we have many cooperators, there will be much probability that cooperators can reproduce. Times, for example, in this shape is easier to see. FC is the payoff, the average payoff of a cooperator at time t. F bar is the average payoff of the entire population. So if the average payoff of cooperators is larger than the average payoff of the population, it means that it's convenient to adopt the strategy of cooperation, and then the density of cooperators will increase. In the opposite case, the density will decrease. All right. This is a dynamical system, and evolutionary stable states are Nash equilibria. Nash equilibria in game theory are the solutions of the games, or the situations in which every player has no reason to change its strategy. Because if changes its strategy, it cannot increase its payoff, unless other players change their strategy too. But it's impossible in a Nash equilibrium to improve that an individual can improve its payoff only changing its strategy. We have this theorem that proves that the evolutionary stable states of this dynamical system are Nash equilibrium. and vice versa, mesh equilibria are evolutionary stable states. So we will focus on prisoner's dilemma again. Why? Because, as I said, we have both temptation to defection and risk in cooperation. So, prisoner's dilemma game, it's the game that most enhance defection. So, in prisoner's dilemma game, there's the less convenience to cooperate. Actually, for two players, the mesh equilibrium is the mutual defection. The rational choice for a player playing a prisoner's dilemma game is the defection. And if we consider a population, a well-mixed population, the equilibrium is the absence of cooperators at C equal to 0. Anyway, we see that global cooperation would be more convenient, because if we compute the total payoff earned by individuals, if everyone cooperates, the payoff would be larger than in the payoff earned when everyone defects. But the equilibrium is the total defection. Here lies the dilemma. Okay, the rational choice is to defect, but if everyone cooperates, the payoff for all the players would be bigger. So this feature makes the prisoner's dilemma game the most useful model for this kind of investigation. So if we see that cooperation appears in a population in some way, then it can be very likely that this is the mechanism that enhances cooperation also in real systems. Okay, we have two different approaches: the theoretical one by solving a replicator equation, and simulation. So we build a population, we have a population of individuals and make it interact. But if we do a simulation, we need some algorithm, some update rule, by means of which individuals can evolve. There are lots of different update rules. For example, here we will use three of them. Replicator dynamics. That is exactly corresponding to the replicator equation in the analytical approach. How does it work? Okay, we choose firstly an individual, then choose a neighbor at random, and the first individual will adopt the strategy of the neighbor if the strategy is larger than the individual, but with probability proportional to the difference between the payoffs. So I have to evolve. I choose a neighbor. If its payoff after a game, of course, the first step is that everyone play the game with its neighbors. Then he needs to decide if evolve, if change strategy. How happens this changement? Okay, I see a neighbor. If its payoff is less than mine, nothing happens. But if it's larger, I will adopt the strategy of this neighbor with a probability proportional to the difference between the payoffs.
The accumulated payoff?
Yeah, no, after each round the system starts from 0.
And then what is the payoff of the previous?
See, the previous. Each round the individuals play and then they check the payoff earned by the neighbors and then evolve if they work. So at the end of each round the payoffs are 0. Yeah, there's no memory. Second possible macroscopic update rule is the unconditional limitation. this is deterministic, almost, see, yes, it's completely deterministic, because an individual chooses the strategy of the neighbor with the largest payoff, if this payoff is larger than the payoff of itself. Otherwise, nothing happens. And then there's the morals rule. This is interesting because the player adopts surely the strategy of one of its neighbors, with probability proportional to the payoff of the neighbor. Of course, the probability to imitate the strategy of the less performant neighbor is very low. And in the opposite case, it's very probable that an individual will adopt the strategy of the best performing neighbor. But in this case, it's not excluded that one can imitate the strategy of a less performant neighbor. So it can happen that an individual imitates the strategy of a neighbor that earned a less payoff. So this is interesting because this rule allows mistakes. Well, okay, let's go back to well-mixed populations. What happens if we solve the replicator equation, or equivalently, we make a simulation of a population playing in a content graph, so everyone can directly interact with everyone else. Mesh equilibria are the stable, evolutionary stable states of this equation. That is that a mesh equilibrium must be a fixed point of this equation and must be a stable fixed point. So, for example, in general we have three fixed points: 0, 1, and a third one, this xe, that depends on the parameters in this way, s over s minus t minus 1. The fixed point 0 and 1 are said pure equilibria or pure fixed point, because in these configurations we have all the players have the same strategy, and then this xe in general is the mixed population. It's a mixed fixed point because in this case, in the population, we find both cooperate in the final state, both cooperators and defectors with densities given by this relation. Okay, harmony game is the game that most enhances cooperation, and actually the only fixed point that is also the equilibrium, so the mesh equilibrium, is 1. So xc, final xc is equal to 1. Everyone cooperates. Prisoner's dilemma, in this case, ends in a frozen state with no cooperators, xc equal to 0. Then we have Stag Hunt. In Stag Hunt, where in general all three fixed points, but the mixed fixed point is not stable, so it's not a mesh equilibrium. And we have two stable fixed points, the two mesh equilibrium, all cooperators or defectors. In which of these two equilibria the system ends depends on the initial conditions. For example, here, initial conditions is always 0.5. So in the initial configuration, half players are cooperators and half are defectors. So it depends on the size of the basin of attraction of this of the two equilibria 0 and 1. In this case, the basin of attraction of cooperation, of total cooperation, is bigger than the other, and so the point 0.5 is included in this basin of attraction, and the system ends up in total cooperation final state. Here, the basin of attraction is of the total defection is bigger, so includes the initial conditions equal to 0.5. Here we have in this case Snowdrift or Octave, where 0 and 1 are not stable, so the unique stable fixed point, the unique Nash equilibrium, is the mixed one, this XE, which depends on S and T, and we see that actually the density, the final density of cooperators is given by the color, and we can check that it's always given by this relation. Well, this, in case of well-mixed populations, that is, in the case of populations playing in a completed graph. What happens in other kind of topologies, Euclidean topology, for example, in a lattice, or in some kind of a random topology, Erdos-Renyi, scale-free, Barabasi-Albert, or small world, for example, Watson-Strogatz. So now we are going to see what happens in these different topologies. First, what happens in a lattice? B-dimensional lattice. This is the work by Novak and May, Nature in '92. Okay, they used in practice they use this payoff matrix. Epsilon is equal to 0. They wrote P1 epsilon 0, but they put epsilon equal to 0. In this case, the game is called the weak prisoner's dilemma, because qualitatively it's equal to a prisoner's dilemma, but we have the zeros in the second column. In the well-mixed population, the equilibrium is the total defection, so everyone defects. It's a prisoner dilemma. But if a population acts on a bidimensional lattice, what happens is that the final state is a frozen state, but has a non-vanishing density of cooperators. So, with this kind of topology, cooperation is not suppressed, but can survive, and the final density depends on the value of t. For example, for t between 1.75 and 1.8, we have the final density of cooperators between 0.7 and 0.95. It's a good density. So, following this result, they suggest, okay, probably it's the topology that can enhance cooperation. But subsequent studies demonstrated that this effect of spatial structure is not so complete. There is no universality. What does it mean? That not always topology, not trivial topology, can enhance cooperation. That there can be other effects that can favor the emergence of cooperative behaviors. For example, in this reference, we see the graph is similar to the previous. We have the coordinate values of the two parameters, T and S. The colors indicate the final density of cooperators. Okay. Here we have in the upper row homogeneous random networks, and the lower row we have regular lattices with the simulations with the replicator rule. So the update rule is the replicator. What happens here that, for example, we can see here the three columns differ for the coordination degree, or the coordination number 4, 6, and 8. For example, here we see that in this part of the area, cooperation actually is enhanced by the Euclidean topology. So respect to the homogeneous random network, cooperation is favored. So the area occupied by total cooperation is bigger, but here is defection that gains over cooperation. So it's a hint that says that it's not so easy to state that, okay, one topology or another can favor cooperation or can suppress cooperation. Moreover, if we change the update rule, for example, here we see what happens in case of unconditional imitation. So when an individual imitates always the best performing neighbor, if this neighbor has a higher payoff. And here we see a completely different picture, completely different with respect to the previous one, but also in general. For example, here we see that in this case cooperation is favored in all the area of the plan TS. So another step is to mixing update rules. These simulations were all the individuals using the same update rule. So, for example, here everyone uses the replicator rule. Here everyone uses the unconditional imitation. What happens if in the population there are individuals using one rule and other individuals using another one? When in this case cooperation is actually enhanced, and what happens if also the rules can evolve? That is, what happens if when a player imitates the strategy of the neighbor, imitates also the update rule this neighbor used in the last round. And in this case we can let the different update rules compete, and we can ask which is the favored update rule. Okay, this is a first picture. Okay, from this reference. Okay, this is a two-dimensional lattice. We have okay the first line, the thick one, the full line is the system with all imitators. So everyone evolves according to unconditional imitation. Is the case of weak prisoner dilemma, s equal to 0, and as a function of t, what happens? Okay, in case we have only imitators, we have this full line behavior. What happens if we add some replicators? So we have in this case the 0.75% of imitators and 25% of replicators. Okay, the thick dashed line FC is the final density of cooperators. The other lines are the final density of cooperators, of imitators cooperators and replicators cooperators. Anyway, we see that in this case cooperation in general is slightly suppressed. So when we have in this case two different update rules acting in the same population, the final cooperation is less than in case of all imitators. Well, this is a study, deeper study. In this case, what have we done? We let the update rules to compete among themselves. So in this case, okay, apart this first row, in the other row are systems where the individuals imitate also the strategy of the neighbor when they have to imitate. Then we let these three different update rules to compete among themselves. First case, unconditional imitation versus replicator, unconditional imitator versus moral, and replicator versus moral. Okay, in this first column, we have the color tells the final cooperator density as a function of the initial density of imitators and B. B is the parameter T. It's weak prisoner dilemma. S equal to 0, T equal to B. In this case, we call B. So, according the value of these parameters, we have the different final configuration. First, this case is a lattice. Here is the static evolution, so the evolved strategies, but not the update rules. The dynamic evolution, also the update rules can evolve. So we see that in general, moral is suppressed, totally suppressed when it's against the replicators, and also with unconditional imitation, the system prefers the moral. Here we have the final density of replicators, here of imitators. In general, we see that cooperation is slightly favored when we have replicators. When imitators and replicators are put in the same system, we have more or less no big change between static and dynamic evolution. But the interesting is when we go to random topologies. This is Erdos-Renyi. Okay, moral again is suppressed, totally suppressed in both cases. While a system with unconditional imitation and replicator, what happens? That the final dynamic case, the final density of strategies is this, where cooperation is slightly suppressed, while the final density of update rules, here the final density of imitators, it's a function of the initial density of imitators and of the temptation, the parameter B. We see that the final density of imitators depends only on the initial density of imitators and very, very slightly on the temptation. And we see, for example, that when it's always the final density of imitators is always less than the initial one. So it seems that replicator dynamics, replicator update rule is favored by the dynamics. What happens in case of scale-free networks? So in case of heterogeneous networks, okay, again, Moran rule is overcome. Always we finish in a final state where in practice we have no Moranist, both when it competes with the replicator then and with conditional limitation. So in practice what we see is a final state here with only imitators and here with only replicators. And we say that imitation seems to favor cooperation in this part when the initial density of imitators is not very high, while in this case when we have replicators the cooperation is favored with small values of the temptation. here. While when we see what happens in a system with imitators and replicators competing, again we have in practice the final density of imitators depends only on the initial one, depends very slightly on the temptation, but here we see that the cooperation is a little bit more than in the case, in the static case. So the competition, it seems that in this case, enhances the emergence of cooperation. Now, just some hint on what happens in small world topology. Okay, this is, in this case we didn't use exactly a small world Watt-Strogatz model. This is a similar but model in which, okay, we start with a regular ring, Euclidean ring, and then we add each missing link with the probability p. So when p is equal to 0, the topology is Euclidean, the ring. When p is equal to 1, we have a complete graph. And then we have intermediate situations. In Watt-Strogatz, in practice, we go from regular topology to Erdos-Renyi, to random topology. In this case, we go from regular to complete graph. This because, okay, the most known results are in the well-mixed case that can be solved analytically. So it's interesting to see what happens tuning from the Euclidean topology to the mean field case. Here it's interesting. Okay, this picture is for one case system of 1,000 individuals. K equal to 1. Is just the number of neighbors in one sense. So in the original ring was made by individuals with 2 neighbors. B 1.05 is the temptation. And in this case, we have only imitators. And we can see that there is a region here where cooperation is mostly enhanced. So here is very low. Here, of course, it's 0, because in this case we have the well-mixed case. And here we have a region where almost every individual in the final set is a cooperator. We can also vary the parameters, so change the value of B, change K, L, and also let the system have different update rules, and we can also make these update rules to compete, so evolving update rules. But anyway, qualitatively the picture is the same. There's a region around 0.01 in which cooperation is mostly enhanced. And this is interesting because in this case, this result shows that the presence of shortcuts, so the missing links of the regular ring that are added, so the shortcuts between different regions or region of the ring, only the presence of these shortcuts can enhance cooperation. In this case, we have no clustering, phenomenon of clustering or hubs, because in this model we don't have this phenomenon. But anyway, cooperation can be enhanced also, in this case, in this region of the parameter P, of the probability of adding linking missing links. If we remember, some here, we see that, okay, in the scale-free topology, if we compare these pictures, cooperation seems to be enhanced more than in the other topologies. So one could think, okay, probably it's the heterogeneity of the network that enhances the emergence of behaviors, but also in this case, where we don't have any clustering effect, we can have a strong enhancement of the cooperation. Okay, the last part. Okay, just to resume about the topology. So topology is a great influence in the evolution of cooperation. Its role is more complex than expected initially, because there are other factors influencing the dynamics of cooperation, as, for example, the update rule we use to let the system evolve. In general, unconditional imitation and replicator seem to be the update rules which must enhance the cooperation, and scale-free seems to be the better topology. But as we have just seen, also in a case of small work with added links, we can have a strong enhancement of cooperation, at least in a region of the probability of adding a link. But this is the most recent work. There is another possible influencing factor. So what happens in discretized time? That is in the case of synchronous updating. The replicator equation is a continuous equation, so the time is a continuous variable. And actually, when we simulate systems, we use correspondingly a complete asynchronous update rule. That is, we pick an individual, let him evolve if it has to evolve, then we pick another one, it changes its strategy in its fields if it has to do that, then another one, and so on. But what happens in the opposite case? So if the evolution is completely synchronous, so we pick an individual, okay, we see, okay, this individual must change. Then we pick another one without changing, and then at the end of the round we change, we update every individual. In this case, a description by discretized time would be better. And the question is if there is a difference in the behavior of the system acting in discretized time and in or in continuous time. This is not just mathematical curiosity, because we know in nature that are species, for example, humans, that reproduce in a continuous way. So every day, new babies are born, and other people die and get married, and so on. But there are other species that reproduce in a discretized way. There are lots of species of insects, some bacteria. What does it mean? That there are species in which the individuals of the old generation die, everyone died, before that the new generation reached the age to reproduce in its time. So it's a discretized evolution. So if in this case we can see a difference in the behavior, it can be important, because so it would mean that we have to distinguish the two cases of a discretized evolution of a continuous one. So we see the first picture. Okay, there are many ways to discretize the dynamics. The simplest is to take the replicator equation and take the discretized version. So it's in practice the first order, we take the first order of derivative and put it in discrete time. So, for example, in this case, the values of the cooperator density at the instant t plus 1 is equal to what we had in the previous time, x ct, plus the replicator equation. This is a map, a unidimensional map. Okay, what is here? Here we have the sign of the Lyapunov exponent of this map according to the values of the parameters t and s. So, in bright, we have the regions where the Lyapunov exponent is negative. So we have a periodic final orbit, or periodic dynamics. Or in dark, we have regions with positive Lyapunov exponents, so the map is a chaotic behavior. If we remember, okay, here, what happens? Here we have only T and S are bounded in this small region, so T between 0 and 2 and S between -1 and 1. And in case of continuous dynamics with the replicator equation, it's enough because qualitatively, if we go outside this region, qualitatively it's the same. So the behavior of the system is the same. So here we have two mesh equilibria, and the final depends on the initial condition. Here the final state is all cooperators. Here all defectors. And here the final state is the mixed state given by this relation. So in the case of map, it corresponds to a periodic solution of a period 1. And actually, here the parameters range in a region much larger. So actually here in the original region where t is between 0 and 1 and s between -1 and 1, we have actually one. The final state is a periodic orbit with period 1, and the final state is exactly the same in the continuous case. But if we go away from the original region, we can find different behaviors. First, periodic solutions, the different, of course, of the continuous of the solutions given by the continuous one that always is one fixed point. So already a periodic orbit is a difference respect the continuous replicator equation. But more, we can see that our chaotic regions. Here we have chaos. In this case, when a system has a chaotic behavior, we cannot say anything about the final state of the system. How will it happen? I don't know. All cooperators or defectors, the system is unpredictable. We must say that in many cases, this chaos is not physical. In the sense that, for example, if the attractor has values, some values of the density larger than 1, of course, this has no physical meaning, because a real system will end with all cooperators, for example, cannot have a density of cooperators greater than 1. But also, in case of not physical chaos, we have influence on the real system. Why? Because, for example, we can have a chaos with not physical values, but some values bigger than 1 and other one smaller than 0. So how can we, in which of these two final state will the system end up? We cannot say because the system will be very sensitive to the initial conditions. And also when the chaos is not physical and is always near the 1.01, for example, if the attractor is slightly 0, or it takes values slightly smaller than 0, slightly bigger than 0. Okay, in this case we say, okay, it's chaotic, but in the real system we can say that for sure the system will end up in the final state with no cooperators. But also the time to reach this final state is very sensitive to the initial conditions, because I can take 2 steps to reach the value, the 0 value, or 20 or 1 million, I don't know. So also in this case, also a not physical chaos can have an influence over the physical system in terms not only of the actual value reached, or actual value of the cooperator density reached by the system, but also in terms of time needed to reach the final state. This is the last one picture. Here we have a case where the parameters t and s are set equal, and we call A. In this case, if we tune A, we have for A bigger than 2.5, we have the case battle of sexes or harmony games here, and 2 bigger than 1, of course. In this case, we have Stag Hunt, but independent from these details, we can see that, okay, in this region, this is the original region usually studied in the case of continuous replicator equation. The system, of course, is not chaotic, it's periodic of period 1. Then, if we go away from this region, we can see some roots of chaos. This is, of course, again, the value of the accumula exponent as a function of this parameter. We see that, okay, in the Stag Hunt region, we have a root to chaos similar to the logistic map. In this other case, the route to chaos is different, and we can also explain quite easily why, but it's not important. And we can see also the change in periodicity. Here, every time the Lefebvre exponent becomes 0 without going to positive values, the periodicity duplicates. For example, here the period is 1, and the final state is exactly the final state given also by the continuous equation. Here the period is 2, and already here the behavior of the continuous equation and of the map start to differ. Here 4, 8, and so on until we reach the chaotic region. And this is a work in progress. We hope to publish something soon. And then we also are studying the case of 3 strategies. So systems with 3 possible strategies. In this case, the chaos can be is more complicated. The attractors are bidimensional. You can see strange attractors and new routes to chaos, but this is a future work. So.
So thanks. If there is any question from the
this last thing that you are doing, I wonder if you could make any relation of the controversy that was already between Nowak and May and Huberman. I mean, the original paper by Nowak and May was called Spatiotemporal Chaos, and it was a synchronous update. Mm-hmm. And then there were a series of papers by Huberman criticizing and saying that all their spatiotemporal chaos was just because they were doing synchronous update. So, is there anything new here? Or?
Well, yeah, here the point is that we always are in the case well mixed, and we discretize the replication. So this is purely totally asynchronous. The correspondent will be purely synchronous evolution dynamics. So in this case, as I suggested before, is that we must think to a population in which, okay, all the individual play and decide to change or not their strategy before the other individuals actually do, and then all together change.
That's what no one made it originally, right?
Yeah, but they only deal in the lattice, and always then only saw what the final paths, the final patterns of the cooperation. They see there's some how cooperators clustered and so on, but they didn't do any quantitative study of this. And actually, because the value of the parameters always is in the original region. So t between -1 and 1, s between 0 and 2. And in this case, already in the well-mixed case, so in total in field or complete graph, the dynamics given by the replicator, the continuous dynamics and the discrete dynamics are equal in complete graph. So another step would be what happens here when we go to these higher values of the parameters back in the lattice. So because they limited themselves on this region of the plane TS, so they didn't see what happens outside. And if already being in the well-mixed case, we see these important differences between the two cases. Also, when we go to other topologies, probably something new will happen.
Yeah. You start with a model that in the continuous time variable x represents a concentration or a fraction of a, so it cannot be larger than 1. Then you go to a map, you say that the map, in the map, the variable x now can take values above 1.
Yeah.
It could take. Yeah. Now, this is something that maybe the map is not that one. I mean, in the sense that if no matter whether you are humans or insects and the time is discrete, the fraction of cooperators in the insects, even if the discrete time cannot be above 100%.
Yes.
So the map, the real map that models that cannot be this one that allows for the larger values of x. It has to be maybe this one conditioned that x cannot be taken a value. So instead of saying, well, these regions here give chaos, but the chaos might not be outside the scope, I say, well, is this the appropriate map model? Or the appropriate map model is not that one, rather than another one that say, first calculate this x and then say, well, but if x is larger than 1, I take 1.
Yeah, actually what, I explain well, but what we do. Okay, if the map is between 0 and 1, it's okay. If, for example, some instant t star is the density is greater than 1, okay, we say that x is final and is 1. And here
so the map that you really simulate is not that one. It's a map that has that plus
yes,
this condition.
but until the density is in this region.
No. This is a clear condition. This condition does not do anything if it is within that range.
Yeah. And what I say is, okay, the real map is this when xc is in this region. If xc assumes a value larger than 1, is set equal to 1 and the dynamic stops, and analogously is set equal to 0 if assumes negative values. This is the real map. So then we go to see what happens in the map that one. And we see, okay, in case of non-physical, for example, let's say not physical chaos. It's a zero that, okay, we start here and then so. Okay, the real, we say okay, the map, the real map behaves so. But the instant star at which the map freezes, which is if it's chaotic, the original map, the map is chaotic. This time depends strongly on the initial condition. So I start very near here, and maybe before I reach the final state, I must go here, or maybe I reach sooner the final state. So also in case of not physical chaos, also these cases can tell us something important about the real map. So for this, it's important for us, at least, to study also regions where the chaos is not physical.
But reaching a trapping condition does not mean it's not physical.
No, it's simple.
So I mean, what would be physical is allowing for the map to continue at negative value and then continue calculating. But reaching a trapping value, I will not call it physical.
But it's something that is not in the continuous dynamics.
Yes, it is. You can go to zero concentration.
No.
Or you can go to 100% cooperators.
In theory, yes, but in this dynamics, no.
Not in finite time.
Not in finite time.
Anything else? So I have a last one. What is the final goal of this? I mean, analyzing different rules, different update rules, different strategies, different topologies, all these kind of things. It is like a never-ending project in general because you can play with so many parameters, and also with respect with the connection to data. How all this compares, I mean, at least I know one recent paper that finally somebody has played the prisoner's dilemma with people in a topology.
Yeah.
So how all this compare all these versus have
to understand the mechanism that establishes cooperation in real systems. So from a theoretical point of view, okay, we analyze all these models and then we can reach some patterns to reach to the cooperation, or we can see how it evolves and so on. From another point of view, we collect data. There are experiments and also so, and then the goal is to see which of these theoretical models better understand the real data. So which are
for example, which strategies or which update rule is more
realistic
and much better than
the experiment did in Cancer last year, and then the goal is, for example, when people interact, which is the real update rule they use. So the people, if change the strategy, use unconditional limitation, or is more similar to a replicator, or sometimes, I don't know, makes mistakes, so it's more similar to Nora, which is the real update rule used by real people, for example. So this is not clear. So the goal is, okay, let's see what happens theoretically, and then compare these results with the experiments, and see what are the theoretical models that better approximate the real data.
But it's hard because there is not a pattern, or I mean, different rules or very similar rules give completely different result. And strategies, similar strategies. I mean, here you only play with strategies that are actions, you know, real strategies that depend on the task. So it seems that is very far. But anyway,
No, it's because the experimental part has just started. So, for example, what we did is to put 64 people in a lattice and then make them play prisoner's dilemma and see dynamics.
Is there anything from the theoretical part that matches that result?
Yeah, for the moment it seems that, okay, it seems because these are first experiments, that okay, the rules is similar to imitation, but it's not really true that we have only cooperators and defectors. The experimental data are better understood if we admit there are strong cooperators, so people that always cooperate independently what others do. Strong defectors, so they defect always. And then some people that cooperate on defects depending on the history, so that has a memory of the past actions. So for the moment, I think they did an experiment last year. I think it's already published.
Okay, so thanks a lot for the talk.